My name is Debbie Stein. I'm the Associate Director for Policy Outreach for the Scott Institute for Energy Innovation. And I'm also Professor of Practice in Engineering and Public Policy. This is our first seminar in our new building, so let's hear a round of applause for the new building. We're very honored today to have Patricia Falcone. I had the honor of working with her when I was at the White House. There she had a very high level position, which was the Associate Director for National Security and International Affairs. Today she is the Deputy Director for Science and Technology at Lawrence Livermore National Laboratory. She came out of that laboratory system. She is also a member of the Board of Trustees of Georgia Tech and also on the advisory committee for Mechanical and Aerospace Engineering at Princeton, and co-chair of the High Performance Computing Initiative at the Council of Competitiveness. She has a Bachelor's of Science and Engineering degree in Aerospace and Mechanical Sciences from Princeton, and Master's and Doctorate in Mechanical Engineering from Stanford. So with that, we'll introduce her presentation, which is called Extreme Curiosity at Lawrence Livermore National Laboratory. And I'm curious as to what is extremely curious at the laboratory.
Thank you. Hi. Well, hi all. Welcome to this room. I'm honored to get to have the chance to be in this gorgeous building. I have been here since Wednesday, and it's just been beautiful the whole time. I'm so impressed. I did have the honor of participating in the President's Frontiers Conference yesterday, and I'm just so fired up. And excited about science and technology, if I wasn't already, if I didn't do it all the time. But you guys are just really lucky to have such great facilities and to have been the site of such a great set of discussions we had yesterday. So I'm really honored to have the chance to tell you a little bit about what I am busy doing now. And so I called it Extreme Curiosity because, and what I thought I would try to do is just talk about national laboratories. I presume that most of you would be students, and maybe as you think about summer internships and places to go to work to really have fun technical careers, that at least one option you should think about are national laboratories if you hadn't already been thinking about them. And so that's what I set out to do. I was going to try to talk some about the system and about some of our programs. I got excited after talking to Debbie this morning about the Scott Institute directly. I emailed a colleague and said, send me more slides on energy. So I added those moments ago. So I think I'm just going to try to go fast, but please, if you've got questions, stop me. But the reason I entitled this is because I think I am someone who has worked in the Department of Energy's National Laboratory System for my whole career, except for the 6 years that I spent at the White House Office of Science and Technology Policy. And I do think it's an environment where you really can satisfy extreme curiosity. So that's why I entitled it. And this is a picture of some cool things that have gone on, and I won't spend time on what it is. Let me tell you to start, before I go back and talk about the system, what it is that we're about at the Lawrence Livermore National Laboratory. And this is a picture of my boss, the lab director, Bill Goldstein. But basically, we are a multidisciplinary national security laboratory run by the Department of Energy. Our mission is to strengthen the nation's security through first world-class science, technology, and engineering. We have 4 broad mission areas that we work in, but maybe it's easier to say that, as this quote from Bill says, is that our work is to diminish the likelihood and impact of war, particularly of nuclear war, of terrorism, of natural and of man-made or human-made disasters through the innovative application of cutting-edge science and engineering. And the broad mission areas that we work in are stockpile stewardship, that is to say the maintenance, updating, and assessment to the President directly on the quality of our nuclear weapons stockpile, all weapons of mass destruction, threat reduction, so defense against any threat that is at sort of the level that it could really affect the nation, and that has high salience S&T, so that where the technical issues and the details of the technical issues really matter. Cross-domain deterrence, which is really the interaction of some of these technologies. That would include defense against nuclear weapons, missile defense, precision effects, space, cyber, also bio threats. And energy and climate security has long been a major area. In fact, our laboratory did the first global climate models that were ever done in the late 1950s, and we lead the current effort that the Department of Energy has for a high fidelity energy climate model. But let me just say something about national laboratories if you haven't thought about it. If you think about a sort of technology readiness level or development, from research to development, pilot, production, scale up, universities like a distinguished university like your own really is oriented in this research, early development, and as partnering with industry to get to the rest of it. National laboratories are created to work sort of in this intermediate area, and really are allocated dollars. We are government owned but operated by folks who are excellent in S&T. Because of doing team science, so bringing disciplines together where people work on doing the science and technology all day, every day, to operate special scientific facilities like big synchrotrons, the Large Hadron Collider in CERN. The U.S. engagement with that is paid for by the Department of Energy, and national laboratory scientists as well as academics are part of it, and to do programs that our taxpayers want done and want to be sure the best science and technology is done as a part of that. And so that includes energy science, that includes applied energy. In our case, it includes a broad set of issues related to national security. But there's not as much of a national lab presence, of course, as universities and industry. There's lots more universities, lots more industry. So, of course, most all our basic research is in universities, and of course industry dominates out here. You'll notice the laboratories go through pilot but are not involved in production at all. The Department of Energy, formally named by Congress, operates the set of laboratories that are called officially national laboratories. There are 17 of them. This picture depicts the different laboratories kind of in a because they're all different. In fact, the granularity is quite different. The smallest laboratory has a budget of, say, about $50 million or less than $100 million. The largest of these laboratories has a budget of $3 billion. So these are not exactly, even some of them are sort of focused single program laboratories, a set of laboratories focused in nuclear physics, particle physics, some laboratories focused directly on energy. Here in Pittsburgh is part of the National Energy Technology Laboratory, which also has its headquarters in Morgantown and another laboratory facility in Albany, Oregon. The larger multi-purpose science laboratories are listed here, and the national security laboratories, which are run by a part of the Department of Energy called the National Nuclear Security Administration. These are the largest of the laboratories. Sandia is the $3 billion laboratory. Lawrence Livermore is the smallest of the three national security labs, but of the whole system, it's the third largest. We are located in the San Francisco Bay Area, east of Silicon Valley. I thought maybe some of you hadn't been there, but I appreciate you have a campus actually there. This is San Francisco sits at the top of this peninsula. This is the Pacific Ocean. Silicon Valley is generally viewed as this area. This is called the peninsula, and so sort of down here is where Silicon Valley is. But this broader Bay Area is all kind of congested in the same kind of traffic mess, but it does include Stanford, University of California, San Francisco. It also includes 4 of DOE's national laboratories. There's SLAC, the SLAC National Accelerator Laboratory operated by Stanford, the Lawrence Berkeley Laboratory run by California Berkeley. We're out here in what's called the East Bay. So not exactly in Silicon Valley, but on the other hand, they draw pictures sometimes where this whole area is called that. And Sandia has a branch office in Livermore that's across the street from us. Also indicated on here are other government. There's one of the NASA 10 NASA centers is in the Bay Area, NASA Ames, which is, I believe, where you all have a campus, as well as a number of other government outposts for R&D, including Lab 41, InQtel, and the new Defense Innovation Unit Experimental. And this is their kind of odd acronym, logo. But just to give you a basis. And so at our lab, we sit on 1 square mile in Livermore, California. It was established in 1952 as Site 200 of the Lawrence Berkeley Laboratory. And then became officially its own lab in 1952. We have approximately 6,500 employees, almost 700 facilities on this 1 square mile, and our budget is about $1.6 billion. It looks like in 17 it's going up. It'll be 1.7. On the other hand, it was bigger a while ago, so we're kind of coming out of a lower time. Our workforce, we're all about doing science and technology, so it is dominated, that 6,500 people, dominated by the technical workforce. So of course it takes to do anything, takes lots of people with lots of disciplines. But these are our technical folks, and you can see, I always like to show this because it is dominated by engineers, but really roughly a third of our technical staff are engineers, almost 20% physicists, and almost 20% mathematics and computer science, and then the remaining third, lots of other disciplines through the lab. So it's really pretty cool. Of our professional and technical staff, we're dominated by PhDs, though plenty of bachelor's and master's level folks. So fundamentally, what we're about in all our mission areas to really answer questions is sort of processes that you will understand well because it's of course part of your training, but that is, balancing, to really get to understanding is balancing really detailed, high precision experiments, integrated experiments if you can possibly do it, and very precise computer models on very fancy computers. So our the biggest job we have is stewardship of the nuclear weapons stockpile, and as I referred to earlier, that is about writing the president. There's sort of 4 big tasks in there, but one of them is what's called annual assessment. So our policy regarding nuclear weapons is that we're not making any more, and we have voluntarily said we're not going to test anymore. So we have a set of weapons in our nuclear weapons stockpile that we don't test. That is to say, we don't blow them up underground in Nevada for the last 20-some years. And but there's a set of technical people have to certify to the president every year what is the quality of these devices. And the point about these is that they are a deterrent weapon. There's no intent to ever use them, but they have to be credible for use because they're basically used to threaten. That is the odd game about deterrence. And so it's a little creepy when you're first thinking about it, I can see. So it would be great fun to talk more about these issues, but our technical people have to say, if you, Mr. President, they're the president's weapons, this is why this is done not in the Department of Defense, but in a civilian agency where it's really about S&T chops, is would these work if they had to work, and will there be, and are they safe? So There's often a phrase about always never. Do they work always when you want them to, and absolutely never under any other circumstance. So it's a very high reliability, really having to know details. So I have to write a letter each year certifying, and so that's quite a big process, and the discipline of uncertainty quantification is part of that, but it's really about the interplay between experiments and computation, making those judgments. There's also a decision from policy that we will life extend these weapons. So when parts are wearing out, how do we continue to sort of nurse them along? Again, we're not making anything new. How do we understand physics questions that remain? And how do we take that knowledge and understand, apply it to a defense and understanding of what's going on? So those are the 4 big tasks. So the stewardship program is really about what can you do experimentally if you can't test. And we have the world's biggest laser that's called the National Ignition Facility that allows us to take very small portions to look at very extremes of energy and temperature. These are regimes that you find in the center of planets and the center of stars. They also turn out to be conditions in which we're interested in looking at physics grand challenges for our main mission. And some of the biggest computers in the world, and the balance between computational modeling and uncertainty quantification approaches using these big models, and really precise experimentation, not just in those 2 things, but in a number of other experimental facilities. So having these specialized research and development facilities is key to doing this work. I talked a little bit about NIF, but it's certainly worth a tour if you ever come. 192 lasers, all the whole facility, the size of 3 football fields, all points to a very small pellet inside a whole ROM that we radiatively heat to get to these extreme conditions of temperature and pressure. Very fancy computers, so NIF, the Livermore Computing Complex, but we also have a number of other specialty facilities that the point of the labs is you're not going to build some of these facilities at more than one place, so the system of DOE laboratories has special facilities, and then those are shared with scientists from around the global scientific community can come and do experiments. We also have a Center for Accelerator Mass Spectrometry that is distinguished at being able to do some of the most precise measurements, as well as a number of other CAMS facilities, including one operated by us, but for National Institutes of Health researchers. We have a forensic science center. We just had a number of results on getting DNA out of hair samples that has been in the press for the last 2 months. A high explosive applications facility, another more training facility on lasers. But what we use these facilities for, and what we nurture, and actually what is my own personal responsibility, is competencies in these 7 areas. And really, just to start at the bottom, that high performance computing using the very biggest computers, the largest number of cores, the most advanced technologies, advanced simulation and data science sort of undergirds everything we do. And the specific technical areas include here, as you can see, high energy density science. So the science, the materials properties, the equation of state of materials at these extremes of temperature and pressure, advanced materials and manufacturing, bioscience and bioengineering, nuclear, chemical, and isotopic science and technology, lasers and optics, and earth and atmospheric science. So what I thought I would do now is talk about some programs, giving you that larger framework on a couple of these technical areas. So we're organized in what we call a matrix, which is that we really focus on the disciplines that support these competencies, and so we have 3 big discipline organization. Each has about 1,000 people assigned to it, and that's generally where our new technical staff come in. One organization is computation, one is engineering, and one is what we call physical and life sciences. And then we have 3 big program organizations, and that is where the interface to the customers and the money for programs come in. And what we do is we expect the discipline organizations, computation, engineering, and physical and life sciences, to be responsible for being at the edge of the discipline and doing basic research and winning awards to do basic work. And then the programs then pull together teams to work on a particular program, and then the teams go back to the disciplines, and then the programs deliver systems often that are integrated, that bring expertise from physical and life sciences and engineering and computation, but maybe they don't want to push. They've got to deliver soon, so they're not really pushing the technology. And what our discipline organizations do is always make sure that we're on the cutting edge, and we bring that cutting edge to the programs, even if sometimes the programs and or the customers don't want to go with the more risky technology. So it's sort of I think the management approach works well. Sometimes it's confusing, this matrix, but it allows you to always be pushing the technology and have attention. So just starting with nuclear, chemical, and isotopic science and technology, I thought I would highlight the fact that in that area we have been responsible with a collaboration with the Fluorov Institute in Dubna, Russia, for discovering 9 elements since 1989, including one that we are particularly proud of, element 116, which is named Livermorium in honor of our laboratory. So actually, often if folks visit, I can give you, we have a little Livermorium pin, and our mayor, the mayor of Livermore, is so pleased about it. But here's some of the folks, and the 3 new elements that were discovered, we're also involved with, and there's tentative names out for those. This one is official. It was named about 3 years ago. I had thought what would be interesting is to talk about bioscience and computing, but then when I got so into the Scott Institute, I added some energy. So I'm going to wing through some things just to tell you about some things we're involved in. And then close. I'm just trying to be clear. So bioengineering, one of the programs that we were a part of, a larger lab project that was funded out of the Office of Science, and all those institutions that are up there on the upper right-hand side for you is something called the Artificial Retina Project, which was in 2013 designated the top, it was the Editor's Choice Award, which basically means it's the top of the Research and Development 100, and was designated by both Popular Science and Time as the invention of the year. What this is an implant, an electrodal ray that is implanted. This is for people who get retinitis pigmentosa and the other one, the age-related macular degeneration. And so that all of the wiring basically works so that if you can get electrical signals to the retina, then the rest of it, communicating to the brain can work. So what this involved was, a lot of technology in terms of modeling and high tech, but what we were involved in was developing these electrodes that actually are implanted and put on the retina, and then connected into the rest of the optical nerve. And then it's wireless technology, and all the rest of the technology is on the glasses then, that has the processing technology, wireless power, and so you can see the implant up there, optic nerve to the brain, and then the rest of the technology is out here, the electronics package and antenna. So what our laboratory did was the implantable device and the electronics package. And what that has led to is that so this is commercially available and is in a number of patients by this company that's there in the middle called Second Sight. And it's also abroad. All the clinical tests were done by other partners in that. But we then have a fab electronics. So this was based on came out of the ability to do the fabrication of these devices, which the first one that was implanted is still, this person is still using it. So these are very long-lived. They've turned out to be very good in this moist environment that is the body, and turns out to be difficult. And what that has led to is a very unique, we have an FDA certified fab capability that has resulted in us being a part of every single one of the DARPA Brain Initiative projects and a number of other projects supported by NIH. And this is a set of projects that are currently ongoing in terms of neural interfaces, electrocardiography, but particularly some of these DARPA projects, both in the haptics work, but particularly now mood disorders and treating PTSD. They are implanting these in folks and mapping by triggering the electrodes. The patients are, these movies are actually quite interesting, changing the mood of folks and understanding what parts of the brain, because the size, I didn't bring any samples, is such that they can cross regions and begin to use this to see where different areas are stimulated affects the mood changes of these PTSD patients. So we partner with surgeons at the University of California at San Francisco. There's also quite a lot of other things that are going on, but this combination of bringing basic science, but also the engineering and fabrication facilities and the ability to partner to get to a product, I thought you would find interesting. The next area I wanted to talk about was about computing. As I pointed out in the competencies areas, we really believe that computing is sort of our big asset, that we bring simulation to every one of our projects. So one of the things that we have really been involved in because of the systems has been predictive simulation. So these are big families of very complicated partial differential equations that you know, of the ilk, but many more of them from doing just pure phenomenological modeling. But where we're really going now with the kinds of problems that we're involved in and the kinds of computing is how do you begin to think about the structures in new computers, and how do you begin to validate with experiments and use neural nets. And our new computers, this is going to be the next computer that we'll get at the end of next year. Our current computers, well, let's see, I was going to say, we have probably a dozen or more supercomputers on our site. Probably overall, we have more than 30 petaflops of computing that are focused, but the biggest computer we have is actually clocked officially for the the Blue Gene Sequoia is at 17 petaflops, and so it came in number 4 in the world rankings in this year's. The first two fastest computers are at a Chinese institutions, and the third at about 17.7 is a computer at Oak Ridge National Laboratory in Tennessee, and ours at about 17, our biggest Sequoia. But we have a number of other computers, as you can see in the petaflop range, that are for different kinds of customers, and and including like this catalyst machine is the start of really looking at modifying nodes so that we have both regular floating point units plus graphical processing units. And then what we're doing next, well, this is just starting to get to some details of things that we are doing in computing and the external recognition that has come with the accomplishments. But what I was going to talk about was starting to think about computing beyond von Neumann architectures. We have a lot of activities going on, but what is fun is we have this brand new neuromorphic board from IBM. This is using their new True North chip. And so now we're beginning to configure systems that have a combination of neuromorphic chips and graphical processing units and floating point systems. One of the advantages to the neuromorphic chips is their low energy use. And one of the limitations of going to bigger and bigger sizes in the computers is the huge energy use. So these mixed systems is what we're doing this fall. This chip was, just talked about, and now we're the only place aside from IBM that has the board. We're working with a number of folks, and there's a number of things we're doing with it. So this is a totally cool thing to be on the frontier of new systems. I wanted to say a little bit about energy and climate. Our energy and climate program is not large in the laboratory, but on the other hand, it's about $100 million, so it's not small as research programs go. It's focused in three big areas: security of energy, reliable delivery, and climate resilience, which gets at climate models. Let me see, these are part of the ones I just added. I wanted to be sure to have that. These Sankey diagrams have been something that the laboratory created some 40 years ago and annually put out, and you can find them for reference documents. The newest version that we're working on, aside from the standard ones that you see that goes from source to use in a fairly clear way, is ones that combines both energy and water use. Those of you who live in such a green area probably don't appreciate the dark brown that we have in California, and the issues of energy and water are very important. So we're moving with the Sankey diagrams there. This continues on energy use. This is just for the state of California. One thing we're doing for the Department of Energy now is a program that's called HPC for Manufacturing. We lead this among the laboratories. This is an opportunity for industry to have access to high-performance computing resources in the Department of Energy laboratories. It's a competitive program. And it comes, it's run by us. It includes Oak Ridge and the Lawrence Berkeley Laboratory. And I thought you would appreciate that at least the first, one of the first industries that's involved in this program using the computational area is the steel industry. U.S. Steel, I know the CEO has visited just recently as part of they've been involved with it for a while. And this virtual blast furnace has been a joint effort over the last couple of years. So perhaps your industrial partners might be interested in this, but the EERE part of the Department of Energy has this competition out. I was going to talk about subsurface science. This is a history of the kinds of things that we have been involved in. Of course, underground nuclear test and trying to interpret signals from tests that other nations might do has resulted in deep knowledge of geoscience and what is going on, but also energy programs, continued. The Department of Energy did a lot of the horizontal drilling techniques that have enabled fracking, and now there is a very large set of programs in the Department of Energy to support current oil and gas programs, and our laboratory is a part of that. We're also doing a series of experiments right now that we call the source physics experiments, and the latest of those was just a day before yesterday, which involve chemical explosions and characterized geometries to try to understand signatures of, basically we're in the business of trying to understand the difference between explosions underground, nuclear explosions underground, and earthquakes, and have been involved. And a lot of that depends on deep understanding of the materials and fracture processes, and it's particularly important now when we are trying to interpret signals, say, from North Korea in recent years, because more and more as those signals are smaller, that is to say there's not as big an explosion, the technical details of just understanding the fracture mechanics as well as understanding the materials really matter. And this is a case where policy links into high salience S&T issues, because when signals are small, uncertainties are large, and if you're making national decisions or waving fingers at other countries, you really have to have your facts right. So there's a lot of very interesting geology and subsurface science that goes on. We're part of a larger system on grid modernization that is led by the Pacific Northwest Laboratory, but a cooperative lab system. One thing in particular that's interesting, this title seems to have come through badly, is we are funded directly by our California Public Utilities Commission to look at security of the grid system in the western U.S., in particular that area that's run by our so-called independent system operator, which is dispatches in California, and looking at both cyber, as you can see here, cybersecurity, and the machine-to-machine work on automated threat response, and grid modeling and simulation to look at metrics. This is, as you can see, it's in partnership with our three largest investor-owned utilities in the state of California: Pacific Gas and Electric, Southern California Edison, and San Diego Gas and Electric, and is paid for out of ratepayer dollars. I mentioned the modeling, ACME modeling, which is the new Department of Energy official model for energy and climate. We're leading. So that's a summary of some technical programs that are going on. I thought I'd just talk about one more thing, which is open innovation. This is something that I know a number of innovation experts, as we try to do a better job of reaping immediate benefits out of investments in the U.S. One of the things we're trying to do is hone our engagement with external entities, including universities, industry, and international partners. This is sort of a picture of what a modern laboratory has to look like. You might think in national security it should have high walls around it. It's also secret. But the fact is, if the science and technology matters, you pretty much know that the best thing we know about really bad science is that it's the kind that's done all closed up without transparency. And what is the case even more now is that you really, if you want to bring the best science and technology to these government missions to make sure we're spending taxpayer dollars wisely, we've got to think about what are the innovation models for doing that in this day and age. And I think this picture depicts sort of a much more open laboratory with much deeper engagement with partners, which brings me to universities. And I'll just say that we have an ongoing set of relationships and believe that university partnerships, certainly with the great universities, are very important to us. We publish that about 50% of our peer-reviewed publications are with university collaborators. We're close to the University of California and have a historic close relationship, so we do publish a lot with them. We have a set of institutes that are a place where we really engage a lot with university collaborators and have specialty programs for those technical areas that are important to us that students can come through. And so, in conclusion, I just wanted to say that if you'd like to work with us or if you'd like to have an internship, that there is a website, or Annie Kirsting is our Director of University Relations. We have programs for undergraduates, for graduate students, for postdocs, and lots of openings for staff. So that is a race through about the Lawrence Livermore National Laboratory, and thank you so much for giving me the chance to introduce it to you.
Great. Thank you very much.